Alright, so this is our final little video, and I just wanted to summarize some of the key points that we've been making, also take it one step further and see how this might look for you if you're going to end up exploring some of these ideas in the future in a future class. So really what we're dealing with here in a lot of these differential equations are drag forces. And in a general sense, you know, air drag is the most commonly thought of drag force, so something falling under the influence of gravity, and it has some sort of drag force resisting that motion. And one of the most popular, most fairly accurate way of modeling the drag force is with some constant times the velocity, so it's changing with respect to velocity. Turns out that when things get going really fast, a more accurate model of the drag force would be a constant times velocity squared. So if you're really going fast, this is where you'd want to go. We'll take a look at that here in a minute. But just a couple other little points with this. So if we use this, we end up with a Newton's second law telling us that mg minus bv equals ma. That's really a differential equation in disguise, because we can write this as dv dt. And if we know that at t equals 0, v equals 0, then initially acceleration equals g. That makes total sense. And then of course what we would imagine is that as t gets bigger, velocity is going to get bigger, so drag force gets bigger, until some magical point where the drag force equals the weight. Because when this happens, if this force is equal to this force, then they tie. There is no net force, there's no more acceleration, you're going as fast as you will ever go, and we call that speed terminal velocity. So this is where you've reached terminal velocity. And how do you solve for that? It's actually pretty straightforward. We're using bv, I'll write it as v sub t now, equals mg. So in this case, terminal velocity equals mg over b. Whatever that constant is, it all depends on how you're modeling this particular fluid flow. Okay, but now we went on. Of course, we did this in a little bit deeper direction. We wanted to look for what velocity with respect to time was, just in a general sense. So in order to find that, we had to solve this differential equation, which I will remind you is that we wrote as mg minus bv equals m dv dt. Solving that using our separation of variables and integration and application of initial conditions gave us something that looked like this. Something like this, that the terminal velocity times 1 minus e to the minus b over mt. Now you notice this guy keeps showing up a lot. Now this, just as a reminder, is just mg over b, so it's just simplified a little bit, but we keep seeing this negative exponential. Sometimes it's 1 minus this, sometimes it's just this exponential just staying by itself all alone. So what is that all about? Well, we can look at this in terms of a graph. Let's draw some graphs here. And what I'm going to do is sort of do 3 graphs, all with respect to time, of different variables, so you can see how they're all related. So let's make this top graph be acceleration, and this one be velocity, and what should we do? Let's do that one. This would be position. Okay. So now if I do my acceleration curve, what would that look like? Well, we talked about that we would start with an acceleration of g, and then it would get less and less and less. So it turned out it would look something like this. This is my acceleration versus time. That's what that curve would look like. Over time, acceleration would get close to 0. That's when we'd hit terminal velocity. So what would our velocity be doing? Well, our velocity would start at 0, that was the initial condition for velocity, and get faster and faster, but tend to reach one maximum limit where a equals 0, and this is terminal velocity. So we're seeing, similar curves. Sometimes they're just flipped upside down. Now what would our x do? Well, x, or y, in this case you might think of it the vertical, as you imagine it, as you're speeding up, you're covering a lot more ground, and eventually you're sort of going to have to level off at some point because you need a slope here that's constant and positive, which is what this graph would tell you. So it's kind of a slightly funkier little bend to it, is all you'd see with that. So those are kind of the three graphs you'd see. So in a general sense, they're similar but different. And in fact, we've got this solution for velocity. Let's take a real quick look. Let's take the derivative of that. Let's do dv dt of this thing. So d dt of all of this mess, vt minus vt e to the minus v over mt, close parentheses. And you might notice, well, if I take the derivative of this little piece, he's just a constant, so he's going to go away. So really, this is d dt of minus terminal velocity e to the minus b over mt. Okay, so far so good. And our velocity we can pull that right out front, minus vt d dt of e to the minus v over mt. And if you remember, there's always some neat little tricks you can do as you get familiar with some of these things, and we can do a little substitution. In this case, if we think, well, what's the derivative of e to the u? The derivative of e to the u is e to the u du, right? So if we allow u to be minus b over mt, the power of that exponent, then du is going to be equal minus b over m, right? Just the derivative of that. So if I take this down here, and I look at this again, basically what this derivative is going to get me is minus vt e to the minus b over mt, but because of my little substitution, I need to correct for this du term, so I got to do minus b over m out here, out front. And I can also remember that my terminal velocity, if I want to get it just all in given values, is mg over b. Okay, so we're getting really close now. So now I can say that acceleration is minus mg over b minus b over m e to the minus b over mt, or to simplify that would be g e to the minus b over mt. That is my acceleration curve, and that makes a lot of sense if you look back up here at what acceleration is doing. Starts at an amplitude of g, that's what we see here, and then it's got this negative exponential decay. So in a general sense, what are you looking for when you look at these types of problems? Because they're always similar but not quite the same. What you're going to find in a lot of these problems is that we have situations where you'll have a solution with 1 minus e to the minus t over something, we'll just call it tau, or you might have e to the minus t over something, we can call it tau too. So really, the shape of the graph at t equals 0 and at t equals infinity really tells you which form you're probably looking at in your solution. So now it's just a last little takeaway, a last little interesting idea to leave you with, is that what do we do if we have our drag force, as I mentioned in the beginning, equal to cv squared? If something's going really, really fast, and that's the way you'd want to model fast things, well, can we find terminal velocity? I think we can, yeah, because that's just weight equal to the drag force. So now it just means terminal velocity isn't that mg over b, it's going to be square root of mg over c. Okay, so that's not so bad to do. But what about if I wanted velocity with respect to time? How does that change? What do I need to do to figure that out? Well, let's real quick run it through and see what happens just for kicks. mg minus cv squared equals m dv dt. Newton's second law. Okay, let me see if I can start grouping things together here. Maybe if I divide by c, mg over c minus v squared equals m over c dv dt. Just trying to separate my variables. And that actually, if you look at that and you look at this, we can really write this as terminal velocity squared minus v squared equals m over c dv dt. Okay, and now I can maybe separate some of these variables. How about if I do it this way? dv over v squared minus v sub t squared equals minus c over m dt. Alright, doesn't look too crazy yet. Now I just got to remember, now I got to integrate from 0 to v of this thing, v squared minus vt squared, and that's going to be equal to minus c over m integral from 0 to t of dt. That's this part. Well, the right hand side, that's pretty cool, right? Minus c over m t. Done. But this doesn't look good, does it? I don't know how to integrate that. In fact, I don't think you're going to find a chart that's going to help you very much. This is a place where what you'd really have to do, and any kind of practical application, is get a numerical approximation. That means you got to ask some software. There's all kinds of different software that can approximate this to well within any region that you'd want it to do, but there's no quick differential equation trick you can use. Some of that software, there's lots of different software packages. Mathematica, which I know some of you are familiar with, is one. Another one's called Maple. That's a pretty good one. Maybe you've heard of MATLAB, something like that. There's a LabVIEW. There's a few of these types of software that could help you solve a problem like that. So it can't all cleanly be done that way, and sometimes you just have to intuitively know what you're looking for and think about what these graphs are doing. So anyway, I hope that summarizes that well, and I hope that can answer some of these questions you might have been having.